Hello everyone. Let's analyze. So today we're going to talk about the L2 inner product space. So our goal is to create a vector space of functions over the interval a to b with the following inner product. Now, while the space of continuous functions might seem like a natural vector space with this inner product, in fact, we see that there are issues. If you have the fortune or misfortune, in a matter of perspective, I suppose, of having taken my course, you've already proved that the vector space of continuous functions is not complete. It has holes. We're going to revisit that today. So we'd like to create a space of functions that contains continuous functions, but is also complete. All right, as we mentioned, we would like for it to contain continuous functions. And the next thing we want to do, and we won't do it in this lecture, is we would like to build a complete orthonormal family for this inner product space. Now, when we talk about completeness and when we talk about complete orthonormal families, both have inherent in their definitions this concept of convergence. So since we're talking about a function space, we're going to talk about sequences of functions or a series of functions that converge or don't converge. And recall that we have different ways of talking about convergence. We have pointwise, which is to say that for every x, the sequence of numbers fn of x converges to f of x. To get into the weeds a bit, when we talk about the for any epsilon there exists an n definition, the n will depend in general not just on epsilon but also on x, and this is pointwise. Uniform convergence means that you can choose an n that works for all x. In other words, for every epsilon there is a big N, and big N can be chosen disregarding the value of x that we're looking for. Another way to view this is that fn of x converges to f of x with respect to the infinity norm or the sup norm. That is, the norm of a function is the supremum of the function over the interval. Now, of course, we know that if the function is continuous, the supremum is achieved and we can replace supremum with maximum. But remember, we're going to expand to spaces that contain more than just continuous functions. And of course, if the supremum of the function over the interval is less than epsilon, then f of x everywhere must therefore be less than epsilon. And there's also in mean, which is to say that fn of x converges to f of x with respect to the norm induced by the inner product at the top of this page. All right, so we say that fn of x converges to f of x in mean. And again, this is, the norm endowed on the space by the inner product. And our goal is to build an inner product space. So convergence in mean is, of course, going to be very important. This is the convergence criteria that's going to determine whether our space is complete. It's going to determine whether a given orthonormal family is complete. So let's take a look at an example. And this is the example here that led us to conclude previously that the space of continuous functions over an interval, in this case 0 to 1, is not complete. So we're going to look at the function that is 2 times x raised to the n power for x less than or equal to a half, and 1 for x greater than a half. Now, as n increases, for x less than a half, 2x is less than 1, and so those numbers are going to decrease. In fact, it should be clear that this function is going to converge to something discontinuous. It's going to converge to 0 if x is less than half, and 1 if x is greater than or equal to half. right? We can kind of see that visually with what's happening. But in what sense do we have convergence, right? In what sense is this arrow here, right? We can kind of visually see the idea, but let's be specific about what sense does fn of x converge to f of x. Certainly, if we look at the difference, we see 2 times x to the nth power for x strictly between 0 and half. And the difference is exactly 0 for x greater than or equal to half or equal to 0. It should be clear from the animation that fn converges to f pointwise. And we can give a brief proof because it's kind of besides the idea. So I'm just going to put the proof on the screen, and you can pause and read it in depth if you'd like to. I would like to point out that this capital N depends on x. So this is important. This is why, right, this indicates that certainly we have pointwise, but not necessarily uniform convergence. Now, we don't have uniform convergence. That's impossible because fn, which is continuous for every n, converges to something discontinuous. And so we know from a previous lecture that it's impossible for fn to converge to f uniformly. Now, what about convergence in the norm induced by the inner product? Because, again, our idea is to build a space with an inner product and the norm induced by it. So in this norm, do we have convergence? Well, certainly we can say that fn is Cauchy with respect to this norm. And in fact, if you are in my course, you've proven this. Therefore, the proof I give here is familiar and old hat to you. But if you're not in my course, and for some reason, watching this video, you can pause here and analyze. So the sequence is Cauchy with respect to the norm induced by the inner product. And it's true that this function converges to f in mean. In other words, it converges to f with respect to the norm induced by the inner product. And that proof is actually a direct consequence of the Lebesgue monotone convergence theorem. This is a theorem that we previously saw. So the proof is straightforward. But here's the issue. F is not in the space we started in. Right? Fn of x is in the space of continuous functions on the interval 0 to 1. But what it converges to is not. In fact, Fn does not converge to any continuous function. So this implies, this example is shows that the space of continuous functions from 0 to 1 is not complete. If we want a complete space, we're going to have to open up our space to discontinuous functions. But what happens when we do that? Let's take a look at another example. Let's consider the sequence of functions fn of x is 1 minus nx for x between 0 and 1 over n, and 0 beyond 1 over n. All right, if we kind of look at the progression of this sequence of functions, right, it's probably pretty clear that this converges to the function that is 1 at 0 and 0 everywhere else, which is, of course, discontinuous. So, again, to briefly talk about the nature of convergence, it's clear that fn converges to f pointwise, and the proof is straightforward. I will point out something interesting, is that in this case, n depends on x, indicating pointwise, but it doesn't depend on epsilon. Fn does not converge to f uniformly because Fn is continuous and f is discontinuous, so it's impossible to have uniform convergence. But what about convergence in the norm induced by the inner product? Well, we know that Fn converges to f in mean, right? It's straightforward to show that the difference between Fn of f in the norm induced by the inner product is less than the square root of 1 over n, which goes to 0 as n goes to infinity. And the proof is straightforward. By definition, this difference squared is the integral from 0 to 1 over n. Now, 0 to 1 over n, but because beyond 1 over n, the value of the difference is 0. So I have 1 minus nx squared. Now, in this interval, this number is less than or equal to 1, so the integrand is less than 1 minus nx. And of course, this is just the area of a triangle of width 1 over n and height 1. So, in fact, that's actually a typo. That should be 1 over 2n, or half of 1 over n. Because they have a triangle half base times height. So that's a typo. This should be actually, and we could say it's strictly less than. Then this would be a true statement. So please forgive the typo. But the conclusion is still true, right? This difference is strictly less than the square root of 1 over n, which goes to 0 as n goes to infinity. But here's the thing. Fn converges to f in mean, but it also converges to 0 in mean as well. I mean, when I say 0, I mean the function that maps every x to 0, because fn minus 0 is also less than 1 over the square root of n, which goes to 0 as n goes to infinity. So fn converges to f in mean, but it also converges to 0 in mean. It converges to two different functions. In fact, the difference of those two functions, f and 0, is 0. Now, in a norm, if something has a norm of 0, then that means that something has to be 0. But the thing is, f is not 0. Almost. But it's not equal to 0 for all x in the closed interval 0 to 1. So that's kind of a problem. We know the space of continuous functions is not complete with respect to our induced norm. We have to include discontinuous functions, but therein lies the rub. If we allow discontinuities, our norm is no longer a norm. Our inner product is no longer an inner product. Remember, one of the rules of an inner product is if I take an inner product of a vector with itself and get 0, then that vector must be 0. But that's not the case for our quote-unquote inner product and our quote-unquote norm, because we could have a function that is non-zero at a single point or a set of single points, and the integral would still be 0. So here's the idea. What we want to do is we want to consider the set of functions for which our quote-unquote norm is finite. Now notice I'm starting to write norm in quotes now, because as we saw, it's no longer a norm unless we fix it somehow. But let's consider functions for which the norm is finite, right? Because if we take the norm of a vector and get infinity, then we have a whole other can of worms. So L2 is the set of all functions that are square integrable over the interval a to b. All right, so this means that the norm of f squared is finite, meaning the norm of f is finite. The problem is that it's possible to have a norm of f equal to 0, but f not equal to 0. However, if the norm of f is equal to 0, we know that f of x almost is 0 for every x in a, b. In other words, the set of x in a, b for which it's not 0 is small in some sense. Well, what do I mean by small? How small? What if it's non-zero at a single number? What if it's not 0 at a set of finite numbers? What if it's not 0 at an infinite set of numbers, and yet the norm of f is 0? So we need to develop some machinery to describe this phenomenon. And this machinery is this concept of measure zero. Now, let me point out now, measure zero is not the same thing as volume zero. We've discussed volume in a previous lecture, and so therefore the volume of a set being zero has a specific definition related to Riemann integrability. Here, we're talking about measure zero, and it's not exactly the same thing. So we say a set has measure zero if for every epsilon greater than zero, there is a family of intervals. Notice a countable family of intervals. So it can be infinite or it can be finite, but countable. But there's a family of intervals such that A is contained in the union of all of these intervals, and the sum of the volume of the intervals, which if they're intervals, the volume of an interval is just the length. So the sum of the length of all intervals is less than epsilon. So just to remind ourselves, the volume, because we're in one dimension, the volume is interpreted as length. Right? One-dimensional volume is length. Two-dimensional volume we typically call area. Three-dimensional volume we typically call volume. And n-dimensional volume is, well, n-dimensional volume. So let's take a look at an example. Let's consider a finite set of points on the real line. Let epsilon be some arbitrary positive number. And so the idea is we're going to make a family of intervals that are centered at each of those discrete points and have a radius of epsilon over 4 divided by the number of points there are. So that when I add them up, the diameter of these intervals is epsilon over 2 divided by the number of points. So when I add it up, I'm going to get epsilon over 2. That's the idea. So again, clearly, if the radius of these intervals is epsilon over 4m, the diameter or the length of these intervals is epsilon over 2m. And because for each xj there's an interval that has xj right in the middle, xj is contained in the jth interval, and A, which is the union of these points, is contained in the union of these intervals. So certainly this finite, which is countable, family of intervals covers A, right? Contains A on the inside. And the sum of their lengths, which we call volume, is the sum from 1 to m of epsilon over 2m. Now notice this sum is not indexed by j, so we can just multiply epsilon over 2m by m, and we get a total volume of half an epsilon, which is strictly less than epsilon. So we see that a finite set, right, a finite set has volume 0. So for example, we know that if a function is 0 everywhere except for a finite set, right, we know already that we can conclude that the integral of this function, or the norm induced by the inner product, is 0. Even though the function itself is not 0 everywhere. It's 0 everywhere except for a set of measure 0. All right, so again, in this case, we've concluded A has measure 0. So I have the definition still there, and I'd like to propose a theorem. Any countable set in R has measure 0. Now remember, a countable set is a set that has a finite number of points, as we just saw, or infinitely many points, but is one-to-one to the set of naturals. So if a set is countably infinite, even though it's infinite, it must have measure 0. And the proof, I'm going to leave as an exercise to the viewer. And if you're in my course, it'll be in your homework. But let me give you an idea. If you have a countably infinite set, the idea is that we have to contain them in intervals whose cumulative length is less than epsilon. Well, the length of each of these intervals, right, has to be some positive number. So could you come up with a infinite sum of positive numbers that sums to 1? So in other words, is there a series whose series terms are all positive and the sum of the series is 1? And if you were to take that series and multiply by half an epsilon, then the sum would be half an epsilon. So then all we have to do is just create intervals centered at our countable points, which we can index by n because there's a one-to-one relationship to the natural numbers. Right, so these intervals are centered at our points and they have a radius given by the terms in our series. So just to give you an idea of how to tackle this problem. So it follows from this theorem that the set 1 over n for all natural numbers n has measure 0 and 0 volume. Now, the 0 volume, that is a result from a previous lecture. So if you're in my course, you've seen that lecture, and if you stumbled upon this video on YouTube for some reason, the lecture is out there. You can find it. Now, it also follows that the set of rational numbers has measure 0 because the set of rational numbers is countably infinite. But the set of rational numbers does not have volume, right? This is a result of how we define Riemann integration, right? There is no, the integral of rational numbers over any interval is not defined using Riemann integration. So notice the set of rational numbers has measure 0, but it does not have volume. The set 1 over n for all natural numbers has measure 0 and 0 volume. Right, just to emphasize that measure 0 and volume 0 are not the same thing. Right, volume 0 requires Riemann integrability and measure 0 does not. So this allows us to define an equivalence relation. In particular, if f and g map the same domain to, let's say, complex numbers, then we say that f is equivalent to g if there's some set of measure 0 for which f of x and g of x agree for every x in my interval except for this set of measure 0. Then we can define the L2 inner product space as the equivalence class of all complex valued square integrable functions over the interval a to b, right, with respect to the equivalence relation defined above. So in other words, L2 is really the quotient set of all square integrable functions, right, over this equivalence class. And now we can, with all confidence and authority, say L2 is an inner product space with the inner product that we mentioned in the very first slide. Because now if the inner product is 0, then in fact f is equal to 0 or it's equivalent to 0. Right? In other words, f equals 0 for all x except for a set of measure 0. So let's return to the sequence. Fn is 1 minus nx for x less than or equal to 1 over n and 0 beyond 1 over n. We know that Fn converges to f point-wise, where f is 1 at 0 and 0 everywhere else. We know that Fn converges to f and Fn converges to 0 in mean, that is, in the norm induced by the inner product. Now, since f equals 0 for all x in the interval except for 0, and because 0 is a set of measure 0, then f is equivalent to the 0 function. So even though this function is not 0 everywhere, we say it's equivalent to the 0 function. It is the same. And now we've removed our obstacles. Now we can say that L2 is in fact a valid vector space, and that the inner product proposed is a valid inner product. And because it's a valid inner product, immediately we know that the norm induced by it is a valid norm. So our next step is, can we develop a complete orthonormal basis for this space? And the answer is yes, and to see what it is, you'll have to tune in to the next lecture. That's it for today.